And I was very excited to be asked to moderate our session today on affect analysis in quantitative ethnography. We have a set of 3 fabulous papers. So just to let everyone know how the session will work, each of our presenters will have 10 minutes to give their presentation. And so we'll do those back to back. And then once our presenters are done, we'll use the rest of the time for question and answer with the audience and the presenters, okay? So I will go ahead and introduce each of the papers, and we'll hear from everyone, and then we'll have some time to chat about their work. So make sure you're writing your questions down as people are presenting. So I'm going to go ahead and introduce our first paper, and what I'm going to do is I'll read the titles of the paper, and then I'm going to let our authors introduce themselves and their co-authors if they would like. So our excuse me, and presenters, obviously, as your papers come up, make sure to share your screens. So our first paper today is going to be studying affect dynamics using epistemic networks.
Thank you. All right, so let me share my screen. Make sure it's all getting good to go. Can you see my screen okay?
Yep, looks good.
All right. My timer. All right. Hi, everyone. Good morning to those of you who are in North America, and good afternoon, good evening to wherever you are, based on where you are. I am Shamya Karumbaya. I am a fourth-year PhD student at University of Pennsylvania. I have my co-author is my advisor, Professor Ryan Baker. He leads the Penn Center for Learning Analytics at UPenn. So today I'll be presenting my work on studying affect dynamics using epistemic networks. Great. So first I'm going to begin with a quick and brief introduction of the field itself of affect dynamics, leading up to the motivation of this particular work, which is affect dynamics with epistemic network analysis. So affect plays an important role in designing adaptive and artificially intelligent educational systems. Research has shown that affect has the ability or has been studied in relationship with important educational constructs like self-efficacy, analytical reasoning, learning, and motivation. Research has shown that affect plays an important role by drawing attention to learning challenges, by appraising learning and guiding cognitive focus. While affect itself is important, developing effective interventions that occur in real time also depends on understanding how affect develops and manifests over time, a field of research called affect dynamics. A large body of research in the past has looked into affect dynamics, particularly looking at the transition between one affective state and another during learning. So affect data collection in an authentic setting like a classroom typically involves direct observation by culturally sensitive trained coders. So the output of such an observation is usually a temporally sequenced codes representing a field observations of student affect. And to conduct affect dynamics analysis, the past research has predominantly used the L statistic. So L statistic basically calculates the likelihood that a student in a given state will transition to the next state given the base rate of the next state. So accordingly, the L statistic value was assumed to be quite intuitive, where L greater than 0 is a transition that's more likely than chance, L less than 0, is more likely than chance, L less than 0 is less likely than chance, and an L value equal to 0 is a transition which is at chance. A recent paper produced a result which is mathematically impossible, where all the transitions into a particular affective state, in this case engaged concentration, were all significantly likely than chance. So we looked into the and we found that this paper, along with a bunch of other papers in the past, have usually had this practice of excluding self transitions. So going back to the previous example we had of the affect data, an affect sequence in these studies where self transitions are excluded are usually transformed, where they remove states where the student remains in the same state for multiple duration. All right, so what happens when self transitions are excluded? So the L statistic assumes that the previous state is independent of the next state. And by removing self transitions, this leads to the violation of this assumption at chance value, because the next state can no longer be previous state because all the self transitions are removed. So in another paper, we go in depth on the mathematical evidence for the statistical error, and we also propose a corrected method which shift the chance value from 0 when self transitions are excluded to a value which is a positive number, and that number is dependent on the number of affective states that are studied. Well, but this temporary fix is non-intuitive to interpret. For instance, if you may have an L result which could be above 0, but it is still statistically significantly below the chance, a situation like this is likely to cause confusion in readers and researchers, and more importantly, lead to incorrect conclusions of statistical significance. All right, so since writing this paper for ICQE, we also did a bunch of other research, and we found basically a host of other issues with L statistics, including issues with high base rates, like imbalanced or skewed affect distribution, issues with shorter affect sequences, and model comparison. So now moving on to affect dynamics with epistemic network analysis. But some of the motivation for us to look at temporal interconnections between affective states using ENA, obviously the first one was to find a way in which we could intuitively visualize the probabilistically likely connections between affective states, but also to sort of explore an area that has majorly been sort of ignored or overlooked in the field of affect dynamics, which is looking at the magnitude of the transition itself, or having multiple active affective states at the same time, and also potentially looking at differences between student subgroups and learning activities, or strengths of connection over time. Before starting our work with ENA, we had to overcome two challenges in using ENA as is. The first was being able to capture directionality in the co-occurrences, because most of the current, the way ENA web currently works is mostly it's a symmetric data. There is no directionality between of the co-occurrences of the codes. The second thing also was to be able to conduct tests not just on the whole network, but on individual edges. This is where we extend ENA to add these additional abilities. So the first one is inspired by what was proposed by Schaffer in 2016, Schaffer and his colleagues in 2016, where in this case of affect dynamics, if you have an affect sequence like this, which corresponds to a transition between the affective states, we could think about the codes not just as these affective codes of, say, engagement, confusion, boredom, frustration, but also as the sender code and the receiver code, like who is the sender and who is the receiver, and accordingly convert these transitions into one hot encoding for the sender state and one hot encoding for the receiver state, leading up to the vector encodings where the directions are preserved. So the first row here, which is a transition from engagement to concentration, you would see that engagement underscore S, which is the sender, is active, and confusion underscore R, which is the receiver, is active. So this was to capture directionality, but we also had to establish significance test for transition strength, and that's where we turn to RENA. RENA allows this. This is also possible in web ENA, but it would require you to go and manually like capture for line weights for each edges. But with RENA, you can at once download all the line weights or for individual units of your epistemic networks that's been developed. So we used this, a very straightforward thing to get the transition strength. And on top of this, we run an one sample two-tailed taste tests. We also normalize these transition weights and conduct a post hoc correction using Benjamin-Hochberg for to account for false discovery rates through multiple comparison. All right, so the other key ENA parameters, we set the unit of analysis as a single student. The conversation is all the observations for a single observation session. And the moving window size is set to 1 because we are interested in transitions. All right, so to see whether or not it works with real data, we conducted a case study using data that we collected from 838 students using assessments as the learning system, which is used for middle school math. Affect data was collected through Baker-Rodrigo Ocampo monitoring protocol, and the affect distribution was as expected, which was pretty skewed towards engaged concentration and then boredom, confusion, and frustration. So this is the L statistic result, and it's obviously from this table, one thing is clear that there are 4 transitions which are significantly likely to occur, and that's after post hoc. What's interesting is if we were not aware of if we were not careful about how we are looking at the L chance value, we would have also called the last 2 as significantly likely, significantly above the chance, because they are positive and they are they have a p-value which would meet the threshold. But we won't be able to do this because the L value at chance is 0.11. So these are actually significantly less likely than chance. And this is the whole motivation for us to be looking at ENA as a way of an alternative approach for conducting affect dynamics research. And we see some promising results because with ENA, the first obvious benefit was visualization, along with being able to see which are the significant or like more significant in that sense, more high co-occurring transitions. We were also able to look at what had a higher transition strength. So you will see in the next slide, among a bunch of significantly likely transitions, 2 of them were most evident, which was boredom to engagement and engagement to boredoms. And this is also what had the highest strength using L statistics as well. Yeah, so this is the results when you look at transition strength, and it looks similar to the structure of the results we saw for L. So with these transition strengths, we see that the 2 that has the highest, which is almost thrice as stronger than the others, are the 2 transitions which also came up as significant, the most with the highest L statistic value with when we did the same analysis with L statistics. All right, so we're going on to some conclusions. The Comparing L statistics and ENA, first with validity, we see that unlike L, ENA makes no independence assumption. So we are hoping that, and we saw that the results were in line with L statistics. So we are ENA, for now, it seems like the results are valid. In terms of interpretability, it's a lot more easier to visualize with a network than keeping in mind what the L chance value is, which may change every time based on the number of affective states you have. We also propose a new approach to run the significance test. So interpretability through that is also, we achieved that through that. I'm going to skip ahead because I know that I've run out of time, so we can come back to this and we can talk later in our Q&A. So also another benefit was that we could have multiple states active at the same time instead of just one state that was active. So in conclusion, there were limitations that we had by using L statistics in affect dynamics research. ENA wasn't we looked at ENA as an alternative approach, and we have seen some promising results. Along with that, we also have to be cautious because ENA is an emerging field, and ENA needs to be vetted thoroughly for its assumption. For specifically for affect dynamics research, we are curious to see if class imbalance, dominance codes, the chance value of the transitions, transition strengths, and also the impact of shorter sequence lengths. Along with this, I hope that this work also has implications beyond affect dynamics for those researchers who are interested to do transition analysis in their context. I hope this work demonstrates a way of using ENA for transition analysis. Thank you, and I'm sorry for taking the extra couple of minutes.
Thank you so much, and I'm sure we will have more discussion about this later. I'm going to move on to our next paper. And our next paper will be incorporating sentiment analysis with epistemic network analysis to enhance discourse analysis of Twitter data.
Okay, is it okay?
Yep, looks good.
Okay, so hello everyone. My name is Camila, and I'm going to share with you the work which is a result of research that we conducted as a result of the last year's data challenge, the QE data challenge connected to the COVID pandemic, where we tried to incorporate sentiment analysis with epistemic network analysis to enhance discourse of Twitter data. And this paper was written by me and also other colleagues, so Jen Siana, Roger Scalisa, Karl Machuska, and David was our supervisor. Twitter, the analysis of Twitter data is quite challenging. There are constraints to the length, how long can the tweet be, that influences the way people express themselves on Twitter. So they use a lot of informal language, a lot of acronyms. They would also express a lot of sarcasm or other ways of internet lingo, which can lead to a lot of interpretation issues if you want to analyze this kind of data. So one popular method to look at Twitter data is sentiment analysis, which is used to identify valence in the text data, and it is used for opinion mining. So when you use sentiment analysis, you get a score for a particular tweet, which would be negative or positive depending on the algorithm that you use, and that would indicate the sentiment in a tweet, which could be positive, negative, or neutral, and it's usually based on expressions or words that are used in this particular tweet. So we followed two research questions in our work. So first we looked at if it's possible actually to combine sentiment analysis and DNA, and if so, how? And the second research question was, if we can combine the two, does it actually give us some different insights into the Twitter discourse than a typical or like a more traditional ENA model alone? So to answer these research questions, we used the COVID-19 tweets dataset, which was open access, and it included English tweets that were filtered by coronavirus, and other synonyms. And we now narrowed our dataset to tweets that were published between March 26 and April 1st, 2020. And it is due to the fact that on the 27th of March in the US, there was an announcement of the biggest stimulus package at this time due to the coronavirus pandemic. So we wanted to look at the discourse around that time on Twitter. And we also wanted in particular to look at the discourse as how it was connected to the political parties in the US. So to do that, we filtered our data by looking at direct mentions and indirect mentions of three politicians that we identified as key people in this pandemic discourse. for the Republicans and for the Democrats. So for the Republicans, it was, of course, Donald Trump, Mike Pence, and Ron DeSantis. And for the Democrats, it was Joe Biden, Bernie Sanders, and Andrew Cuomo. So we filtered the data by the direct mentions, so the tweets that were directed at the politicians, but also we looked at the text of the tweets, and we identified some phrases that people use to mention this politician in the tweets. Also, we looked at ways that people would talk about these parties or people who support these parties. And because we looked at Twitter, we had to use both neutral and also pejorative terms to describe the parties. So the way we looked at the data was that if in a tweet there were more mentions, direct or indirect, directed at the Republicans, the tweet would be classified as Republican. If there were more mentions on the Democrats, then it would be classified as Democrat. And if there was a same number of mentions of Republicans and Democrats, then it would go into the group called balanced, which was also part of our data set. But we didn't really look at the differences there too much. So after we filtered our data set, we started the coding process. We were 4 coders. So we took a couple of samples of the tweets that we had, and we used a bottom-up approach to see what kind of themes can we see in the discourse. And after multiple iterations, we came up with those 6 codes that you can see on the screen. So vulnerable workers, high-risk people, stimulus action, reopening, lockdown, and China involvement. And then we validated our regular expressions using the encoder. So in the next step, we eliminated the tweets that were not coded. We also eliminated duplicated tweets so that we have a manageable data set that we can work with. And we ended up with 4,944 tweets. And we used the web tool to generate the ENA networks. So at this stage, we also used a sentiment analysis algorithm that was based on the Affine lexicon-based model that was specifically developed for social media and microblogging. So it was an R package that we used, and by using this sentiment analysis algorithm, we got the following distribution of the tweets. So as you can see, there were many negative tweets, or our analysis was a bit skewed towards the overrepresentation of the tweets that were talking about or directed at Republicans. And the reason for that was Donald Trump, because there were many tweets talking about him or directed at him in our data set. So we developed 3 models. This is the first one, which doesn't include sentiment analysis. All the models have 3 groups, as I mentioned before: Republicans, Democrats, and the balance group. The balance group is hidden from the models, but it's included in the model in the background. So we really focused on the differences between the tweets talking about or directed at Republicans and the Democrats. Republicans are represented by red, and the Democrats are represented by blue. And our unit of conversation were the individual tweets for all the models. And the reason for that is because of our filtering process, we were not able to identify threads in our data set. So this is the first model that we got. The second model included the sentiment analysis. And in this model, sentiment analysis was part of the blocking variable. So it was part of our segmentation of the data, where we grouped the data not only by the tweets directed or talking about the Republicans, but also only by the tweets that were, for example, positive for our first model in the model 2. And only neutral sentiment tweets, and then the negative tweets in the third one. And then our third model included sentiment analysis, but as codes. So the grouping is the same as in the first model. But as you can see on the screen, we have neutral, positive, and negative as codes in our network. So what we have found out is that our second model, so the model that used sentiment analysis as a blocking variable, had the highest variance explained and the highest co-registration correlation of both axes. Also, it helped us better understand the differences between the groups. So we had some connections that were only prevalent for a certain sentiment, which was not visible in the model when there was no sentiment included as a blocking variable. And our third model, so the model that included sentiment analysis as codes, actually expanded our data set because of the nature of Twitter and the short tweets. Many of our tweets were coded only with one code, which meant that they were excluded from our analysis because there were no connections within this one unit of analysis, this one conversation. So by adding sentiment analysis, we're actually able to include them into the model and through that expand our understanding of the discourse. On the other hand, however, we also were aware that sentiment analysis or the scores that we get were only a number, which means that we had to assume what does it actually mean to get -2 or +1, or as even more simplified it by calling it positive, negative, or neutral. So what does it actually mean that a tweet is positive? What does it actually mean that it's negative? What is actually behind this algorithm that gives us the score? And at the same time, also in QE community or in general, validation is very important. So we could have actually built the coding, the sentiment coding ourselves. We didn't do it. We just relied on an automated algorithm, which means that we got some numbers or some coding which was not validated as required in the traditional grounded coding approach. But in conclusion, we can say that what we found out is through looking at the different models, including the sentiment analysis in a different ways, we got some different insights into the discourse and into the data. However, it's very important to think about this validation problem, which might be something for future work, how to include sentiment analysis more meaningfully into the QE. And at the same time, we can see that there's a potential to incorporate new tools, which are actually not really new, they're well established, but in other fields like sentiment analysis, and how actually can we put it together with ENA and maybe speed up some process of coding, but do it in a cautious way. Okay, that's it from my side. Thank you.
Thank you very much. Great presentation. I'm going to move on to our last paper of the session. And the title is Student Emotions in the Shift to Online Learning During the COVID-19 Pandemic. All right, looks good.
Okay. Hello, everyone. Good morning or good afternoon, good evening, wherever you may be. My name is Tiffany Wright, and I will be presenting on student emotions and the shift to online learning during the COVID-19 pandemic. I'm presenting on behalf of our team, Danielle Espino, who is in the room with us, and Victoria Brown, Matthew Sweeney, Zachary Mbasu, and Sung Lee. The first university represented is Pepperdine University, and also our colleague Zachariah Mbasu is from Africa Mass Initiative in Kenya. Sorry, one second. Trying to advance the slide. Here we go. Okay. So similar to Camilla, our research came out of the data challenge last April. So we actually worked together with a few other colleagues on a poster, but we got together and tried to think about what other challenges were we seeing during the COVID-19 pandemic. And quite a few of us on the team were interested in looking at education and some factors for online learning that were impacting students. So the team decided we wanted to go this route in terms of our next research project of the paper. So the study examines the students' emotional responses and how they were adjusting to online learning. We looked at the New York Times, the Learning Network section, and we collected data from a prompt that the students posted. And as you can see here, this was it. Excuse me. This was the prompt that they responded to. So it was open to any students. They just had to put what school they were from. A lot of them did happen to be from the East Coast, but they were from other states as well. Okay, and just an overview of the paper. So I already gave the prompt in the previous slide, but just to give you more information regarding the time period. So the prompt was posted by the New York Times on March 30th. So the students were responding anywhere between March 30th and May the 5th. There were 356 total responses examined. So we did have to take out some responses to the initial comments. We just wanted to see what were the initial comments that students were posting. A lot of the comments were just repeating what the initial student said, so we didn't want to look at that. And we did delete a few duplicates. As far as the participants, they were middle and high school students aged 13 and older. We did a grounded analysis of the data, which yielded 6 factors looking at focus, instructional format, workload, schedule, peer interaction, teacher interaction. And in later slides, you'll see our code book and how those matched up to my next point of emotions. So we also looked at what were the positive emotions and what were the negative emotions that students were experiencing. And we pulled from Peckrun's Wheel of Emotions and a study by Kim and Niederpep regarding student emotions in response to the H1N1 crisis. In terms of our methods, we did do coding in teams of 2. So all of the authors were also coding. We coded individually, and then we got together with our pair to do a process of social moderation for agreement on final coding. We coded concurrently for construct and emotion. So for example, there could be one construct such as format, but it might be a negative and a negative and a positive emotion associated. There were some where maybe they had 2 positive emotions depending on what the student said in the utterance. And I'll show an example of the utterance shortly. And we use epistemic network analysis to utilize, excuse me, I put duplicate things there, sorry. We utilize it to examine student emotions in relation to online learning dimensions. And I'll show the positive and the negative valence shortly. So here's an example of our code book. I won't go into too much detail, but I will just say that within certain constructs, this is the case for the online learning factors as well as the negative and positive emotions. We did have to group many items together. So for example, you'll see with focus, not only is it focus in the way that we would typically think of the word focus, but also were the students motivated, were they engaged, how protective were they? So grouping very similar qualities into the one construct just for the sake of not having billions of codes that we had to code for. And here is the negative and the positive emotion chart. So the red are the representing the negative emotions, anger, fear, sadness, and anxiety. Very similar, we had to group certain aspects together. As you'll notice, anger, that also would include irritation and annoyance. So again, not the traditional word anger that we'd be used to, but just grouping for an overall theme. And for positive emotions, gratitude, interest, hope, and compassion. So here's an example of how we coded the utterances. So one student said, although online schooling has required a lot of screen time, is a pain to use, and makes focusing hard, I'm grateful to have my afternoons off. So as you'll see, the first highlighted portion of this utterance they're talking about format in online schooling. And we coded for anger because they're expressing frustration through it's a pain to use. And then the next line, representing focus and anxiety. And then the last line, they're showing or they're expressing something positive in that they're grateful to have a flexible schedule. So our results showed that there was heavier emphasis on the negative emotions. We do think, and we'll talk about this very briefly in the discussion section, but we do think there was a lot more negative emotions showing because these responses came in fairly towards the beginning of when the pandemic hit the USA. So a lot of these students were very abruptly shifted into online learning, which could account for why they might have had more negative feelings about it than positive. It was very new. So our results here are showing what I've just mentioned in the other slide about seeing more connections within the negative aspects. So as you can see here, focus, format, schedule, um, lots more connections being made with the negative aspects. Some being made on the positive side, which are highlighted in blue, but those connections are a little less prevalent. We did use a 0.2 edge weight just to show the more salient connections a little bit more clearly. So just a little tweaking that we did just to highlight the connections that were more prominent. And then here we just disaggregated for positive and negative. So as you can see, format and schedule, we're showing strong connections. And as you can see over here on the negative side, very, very strong connections, especially here, for example, anxiety. So lots of anxiety being reported around their workload, their ability to focus, and the format of student online learning. So just some takeaways. I think I had covered this in a few slides, so I don't want to be too repetitive, but this idea of more focus being on the negative emotions. And then I mentioned the sudden change. So change in, their usual routines. I didn't talk a lot about teacher support or peer interaction, but we did look at that in the paper. So a lot of students were saying they missed their friends, they missed their teachers. It wasn't the same working remotely because a teacher wasn't there to keep them accountable. So those are just some examples of some routines and processes that they either directly reported missing or that might have been kind of subtly there in the text. Limitations, we did only focus on learning factors. So for instance, something like socioeconomic factors that might have impacted their learning, such as different family dynamics that change as a result of the pandemic or financial factors that change in the household. Those aspects weren't represented. In terms of future work, we may look at something like what we mentioned in the limitations. Maybe it would be expanded beyond the traditional factors of learning that we had in our code book, but maybe it would expand out to other factors that influence learning, but maybe aren't directly related, just to see how that impacts students' experience in the classroom. And one key element that we would think about taking a look at is where are the students almost 1 year later? So now we're in February 2021, and we're almost maybe like about next month would make it a year out, at least here in the US, in terms of when the shift happened, when everyone went online. So we'd be interested in seeing, are the students still reporting primarily negative emotions? Have they adjusted to where more positive connections would come out? That's something that we think would be very interesting to take a look at as time has evolved within this pandemic space. Okay, well, that concludes our presentation. You can feel free to contact me at my email address below. I can put that in the chat if anyone would like it. And then also Danielle Spino, my colleague, you can contact her as well. Thank you.
Thank you very much. Wonderful presentation. So now we have 20 minutes to engage in some Q&A with our authors. If you feel like turning your camera on, that is always encouraged. If you're not feeling camera ready, I understand that as well. So you can, if you prefer to put your question in the chat, I'm happy to read those. Otherwise, please feel free to unmute and ask questions of our authors.
Sarah, I appreciate all three of the presentations and learned an awful lot from them. I did have a back channel conversation with Shamya asking about the nature of the definition for self-transition. And she replied, Shamya, I don't know if that might be useful for you to do a quick recap of self-transition as something that's not actually at the agency of the student necessarily, but its role and its significance.
Yeah, absolutely. Yeah, so self-transition is sort of like is a misnomer in that sense that like the student is not really transitioning, the student is just staying where they are. So if they're watching lecture, they are staying watching lecture. If they are confused, they are confused. So the reason we use self-transition is I think is a term borrowed from computer science and math, like with Markov modeling, for instance. We always talk about self-transitions. So in practical terms, the decision on whether or not at least in research, whether or not you include or exclude self-transition, I think comes down to whether you're interested in the persistence of a state, or if you're interested in mostly looking at how one state transitions to a new state. So the first one may be more important when you're designing an intervention. The second may be more important when you're building a theoretical model, for instance. So yeah.
Thank you.
I have a question for Shamia. That's a wonderful presentation. I like the way how you construct the directed in your way. That's smart. One question I have is, I know that's beyond the scope of your paper, but I'm just thinking, you said the window size to be 1. The reason is that you are only consider the previous to next, right? But what if you want to explore further, deeper? I want to consider the previous to the next.
Yeah.
Can we is there any simple way to just set the window size to be larger to include those things? This just yeah. I think that could be something for future research, but I want to know what your view on this.
Absolutely. First of all, I want to give credit where it is due. So although I think this is one of the first applications trying this approach, the idea of sender and receiver was discussed by Schaffer in his tutorial. He mentioned that at the end of his the epistemic network analysis tutorial. But yeah, all right. So the question on the sliding windows, I agree with you. There is so many interesting things we could do, and we talk about it in our discussion as well in the paper, where we not just transitions, but also just looking at co-occurrences in a larger time window. There's always question about when you look at affective states, what's the grain size? Like, are you interested in micro emotions or macro emotions? How much does it matter that the student was very briefly frustrated as opposed to was, so there's a lot of interesting ways in which we could think about the role of constructing a larger moving window size. Just in terms of, I think, multi-state transition, which is also a research that has been done in affect dynamics. People usually look at engagement, confusion, frustration, boredom as a potential multi-state transition to see how, that's one of the popular multi-state transitions that has been explored. In that sense, I think my personal way of doing that would be to code it in a way that each of those transitions is denoted in a single vector representation, so that when you look at one vector, you have all of those transitions together, instead of for that specific case looking at larger moving window size. But there are many other, I'm sure, uses of exploring a higher window size. Thank you for the question.
So in the chat, there's a question for Tiffany that I'll read. And that's from Eric. Coding two affective states in one utterance makes sense. Presumably, a student could convey more than two. Also, is it necessary to identify or label positive or negative? Thinking of anxiety, which could be either.
Thank you, Dr. Hamilton. I'm kind of hooking on the second part of the question because that's very interesting, but I'll answer it in order. You had mentioned about the student having more than two. Yes, we did see a few cases of that with longer utterances. Some students had maybe like 2 sentences or so response. Some had whole paragraphs. I guess they wanted everyone to know how they felt about remote learning. So we did see that happening. And then just to think back to the coding process, I remember there were students that would say something like, oh, I'm so frustrated, I can't concentrate, multiple things. And they would turn around and say, but the bright side is I have more time with family. And then they would go into a longer detail of that. So I think some of the students that were more detailed, I did notice that there were multiple, like you said, possibly even more than two in one, I would say in one thought, maybe not necessarily one sentence. And the second portion about maybe more neutral emotions, that's a good point about anxiety could be something that's more neutral. We did in the coding process at one point code for, and Danielle and Sun, feel free to jump in if I'm not recalling 100% correctly, but I do remember there were some emotions where we had to code it as neutral because it wasn't necessarily positive or negative, but it was more so coded neutral for um, maybe their overall thought. But I would say if we identified one emotion, say anger, I think within the social moderation process, we kind of had a more in-depth discussion to say, are we going to label this one way or another? But for a future study, it would be interesting to maybe look at different categories of, say, anxiety or anger sounds so so heavy. So I'll say frustration, and maybe, was there ever frustration that led to a positive and that it showed that the student wanted to be challenged, or for instance. Sung or Danielle, I don't know if you would like to add anything.
Thank you. That was very helpful.
Okay, we have another question in the chat. One question for Camila and Tiffany at least. Can you expand on where, when, why would you use sentiment or emotions as a code versus as grouping variables? And saying that this is from Luis saying that he had a similar problem in a recent data set.
Okay, so the way we decided this is, so we looked at the very specific data, which was very short text. So adding sentiment to include more of the tweets, that would be where I would think it would be the best to include it as a code. It has its limitations, of course, but yeah, I think that would be the best. As a grouping variable, I think it was interesting actually for us to use it just to zoom in on the different groups. So I think if you have a data that where you, when you just get the aggregate, and you would like to see, for example, okay, but so let's, sorry, from the beginning. So for example, in our case, what we found was that there were certain connections between the codes that were apparent only for a particular sentiment for a group. So for example, in the tweets talking about the Republicans, for example, there would be a certain connection which was very strong in the aggregated graph. But then when we split it into several sentiments, it was apparent that it's only true for particular sentiments, not all of them. So in this case, that would be useful to see more detailed actually, okay, so we add this another layer of looking at the data in more, when it's more specific. As a code, it's quite tricky because the more codes you add, in general, it's not really helpful because then it can be too many. So I would be cautious with that. But as I said, it was only useful in our case because we had so many tweets that were only with one code, which might be a limitation of our coding. So that's also another option there. I don't know if Jen or Rogers, if he's still here. Yeah, yes, he's still here. If you want to add something, then please jump in.
I can go ahead if I was just waiting to see if the other team wanted to add. If not, I can respond for our team. So for our team, I would say in terms of the grouping variable versus codes, I think we had limitations with our data since it was a secondary analysis. We were working with what we were able to gather from the New York Times. So we didn't know as much about, say, the population to be able to expand on what were the demographics, say, if we looked at that within and placed emotions below those groupings. So I think coding was, I guess it was more efficient for us because we only had set information about the students. The emotions actually probably were the most information that we knew about them outside of obvious things like name and school that they reported. So, and also I wanted to mention that the frameworks that we use from the Kim and Niederpep study about H1N1 and student crisis, that guided us to the coding route as well, just in looking at how that paper examined students. So just kind of that guiding framework that we have helped a lot in determining to use codes.
I'll jump in just for a second because I was thinking of one example that we ran into while we were working. I worked with Camila and Rogers on Twitter data and the political parties. And I think that one really useful implementation for using affect as a blocking variable or as a grouping variable is that you can actually pick apart your other groups to look for similarities when they have different feelings about things. So for example, one of the things we were looking for is, as we're looking at Republicans and Democrats, were positive Republican tweets actually the same as positive Democratic tweets? Or were they the same as negative Democrat tweets, which was kind of what we expected? And so by taking those two larger groups and being able to split them by affect, or by sentiment rather, it allowed us to really make some comparisons about like what were the true nature of the argument and how did sentiment play into it, as opposed to just like which concepts, for example, are related to being positive or negative when using it as a code.
Thank you. We probably have time for one more question for our authors.
Okay, I have a question, Tiffany. Near the end of your presentation, I seem to see that you run two different ENA models for positive and negative separately. Oh, is that right? Okay.
Yes.
So what I'm thinking, if you run two different ENA models, of course you cannot compare. I know you compared the connectivities, but I feel like probably we ignored one important thing, that's the node positions. That is how the nodes positioned in the space. So the two graphs, you will see the nodes are positioned in a very different way. So in one graph, you see some are close to each other. On the other graph, they are far away from each other. I don't know if that can tell us more information about the story.
I see. Yeah, I definitely think that's something that we could look at, especially moving forward, because that makes sense what you're saying. I'm just processing it as your comment. Like you said, how that tells the story, especially when we separate it, because negative did look vastly different than what we showed for the positive when we separated it out. So thank you for that suggestion. That's very helpful.
We do have a couple minutes left. I'm going to go ahead and ask a question if no one minds. So I really enjoyed this session. Sentiment analysis is something that is new to me that I'm trying to figure out. You know, and I know that we often separate into positive, negative, and neutral, but I think in some forms it's possible to look at the balance, or, you know, how positive or negative something is. And I'm just, maybe this is a naive question, but I'm just wondering what the authors think about that, and if there's potentially a way to incorporate, you know, the degree of sentiment or feeling into the analysis, or if that would even be useful.
Yeah, I mean, I think it's an interesting question, and I was thinking about it as well. I don't know about ENA because I know that there are, okay, but this is just my understanding of ENA. Sometimes if you want to use weighted values, you have to change the whole coding in a way. So far I understood it cannot be combined binary and weighted. So I think there might be some issues there, but I think it comes back to the interpretation problems in a way. What does it mean that something is +2 out of 5, +5 positive? So, but I mean, I don't know, like there must be a middle way there, because on one hand, sentiment analysis is based on lexicons, which means that they already have the regular expressions that are behind it to build those sentiments. And that's how they weight every word in a sentence. And that's how you get the score at the end. I mean, in the simplest terms, there are some other ways, I'm sure, to do it. So it's like the same way we would code. So we are kind of reinventing the wheel, but what we do as well is validating it. So I'm wondering if there's a way to find the middle ground of using those lexicons that are already out there, but trying to incorporate it in a way that, but then you have to have a very deep understanding, I think, of how they work. And I'm not sure if the score way is the best way, though the number might be a tricky thing.
This may be a little more straightforward in my context, because it's likely, especially if you're doing like for affect data collection, if you are having self-reports from students, or if you're having retrospective affect judgments from the students themselves, instead of asking them, which among these emotions are you feeling? Are you feeling confused, frustrated, bored, or X, Y, and Z? Or maybe even just positive, negative. Could also be a survey which is five scale, like a Likert scale, right? Which basically could give you, in that sense. I don't know, with field observations, I have never seen, with the protocol that has been around for almost a decade, I haven't seen valence being coded specifically. So that's about data collection. I can see, or even with detectors, automated detectors, we can look at the probability that the detector gives. You can have like different thresholds for under 0.3 as like not confident could be a way of like interpreting like not strong emotion in something. Maybe true with like text as well. If you're doing an automated detection in text and a model says that it's only confident 0.3 versus 0.8, do we put them all in one bucket or should we be looking at them separately? I think that's a very interesting question. And in terms of the in terms of ENA itself and how we can change those binary codings to weighted codes and how that would then yeah, it's basically an interesting question, and I think there is something there.
Well, thank you. And thank you all for wonderful presentations and a wonderful discussion. We're at time, but I know there is a coffee break now in the conference for folks to continue their conversations. And I am sure I will see you all in another session. Thank you.